Hello everyone. As promised in the previous video on NMR spectroscopy or PMR spectroscopy, we are back with another exciting and informative video on water and its treatment. Thanks again for supporting the second video of the series on spectroscopy. Your likes, shares and subscriptions are highly appreciated. From your response, it is once again very clear that interaction method or question-answer method is better than many other methods of learning. This is a long video. Please watch the entire video to learn all aspects of NMR spectroscopy. You can learn the topic clearly only if you watch this video till end. Let's start. The topic of the video is water and its treatment. The first question is, define water. The answer to this question is, water is a chemical substance composed of hydrogen and oxygen. Its chemical formula is H2O. Water is one of the fundamental needs and is essential for life. Water is the most abundant and vital substance on earth. Water is a polar molecule, which means it has a partial positive charge on one side and a partial negative charge on the other. This is shown in the figure. It exists naturally in all three states: solid in the form of ice, liquid in the form that we see around, and used for carrying out many of our daily activities such as cooking, cleaning, and bathing, and gas in the form of steam. The next question is, question number 2. Why is water called the universal solvent? The answer to this question is, water is called the universal solvent because it can dissolve more substances than any other liquid. This is due to its polar nature, where the positive and negative ends attract different ions and molecules, making it capable of dissolving a wide variety of substances, including salts, sugars, acids, alkalis, and gases. The next question is, question number 3. What are the physical states of water at different temperatures? The answer to this question is, water exists in 3 physical states: solid, ice, snow, hail, etc. Water exists in this state when the temperature is below 0 degrees Celsius. Liquid. Water exists in this state when the temperature is between 0 degrees Celsius and 100 degrees Celsius. Here, 0 degrees Celsius is the freezing temperature of the water or melting point of the ice, and 100 degrees Celsius is the boiling point of water. The difference in the two temperature is called liquid range. This means water maintains its liquid state for 100 degrees. Gas, steam or vapor above 100 degrees Celsius. The next question is, question number 4. List the various sources of water. The answer to this question is, the various sources of water are: surface water. Water that is found on the surface of the earth is called surface water. Most common sources to obtain this type of water are rain, rivers, lakes and sea. The water obtained from these sources is called rainwater, river water, lake water, and sea water, respectively. Underground water. Water that is found below the surface of the earth or underneath the earth is called underground water. Most common sources to obtain this type of water are springs, wells, etc. The water obtained from these sources is called spring water and well water, respectively. The next question is, question number 5. Why is rainwater considered as the purest form of natural water? The answer to this question is, rainwater is considered as the purest form of natural water because during the process of vaporization by the sun, impurities and salts do not evaporate and are left behind. The vapor condenses to form water droplets that fall as rain. However, as rainwater passes through the atmosphere, it may dissolve gases like carbon dioxide, CO2, sulfur dioxide, SO2, and nitrogen oxides, NOx, making it slightly acidic. The next question is question number 6. What happens when rainwater falls through the atmosphere? The answer to this question is as rainwater falls through the atmosphere, it dissolves gases such as carbon dioxide, sulfur dioxide, and nitrogen oxides, which form weak acids like carbonic acid, H2CO3, sulfurous acid, H2SO3, and nitric acid, HNO3. This makes the rainwater slightly acidic. The next question is question number 7. Define river water and its composition. The answer to this question is river water is a naturally flowing watercourse that typically contains fresh water moving towards a sea, lake, or another river. It is nourished by precipitation, surface runoff, springs, or glacier melt. River water contains dissolved minerals such as NaCl, KCl, NaNO3CaCO3 and Na8CO3. The next question is question number 8. How is lake water different from river water in terms of composition? The answer to this question is lake water, unlike river water, is relatively stagnant or slowly moving and occupies an inland basin. It contains lesser amounts of dissolved minerals but has a considerable amount of suspended and organic matter, such as plant debris and microorganisms, making its composition different from that of river water. The next question is question number 9. What are the main dissolved minerals found in seawater? The answer to this question is seawater contains approximately 3.5% dissolved minerals. The major dissolved minerals are sodium chloride, NaCl, makes up about 2.5% of the total dissolved minerals. Other dissolved minerals include magnesium, calcium, potassium, sulfate, and bicarbonate. Seawater also contains dissolved gases such as nitrogen, oxygen, carbon dioxide, and noble gases. The next question is question number 10. What is the approximate percentage of dissolved minerals in seawater? The answer to this question is seawater contains about 3.5% dissolved minerals, with sodium chloride, NaCl, contributing approximately 2.5% of the total dissolved content. The next question is question number 11. What is groundwater and how is it replenished? The answer to this question is groundwater is water that exists below the Earth's surface, occupying void spaces in soils or geological strata. It is replenished naturally by rain and snowmelt, which seep down into the ground through cracks and crevices, a process known as infiltration. The next question is question number 12. Differentiate between spring water and well water. The answer to this question is spring water naturally flows from an underground source to the Earth's surface. It is relatively clear and contains high levels of minerals like calcium, magnesium, and sodium, making it hard water. Well water, obtained by drilling into the ground to access groundwater. It also contains dissolved minerals and organic matter, depending on the surrounding geological conditions. The next question is question number 13. What is soft water? Give examples. The answer to this question is soft water is water that easily forms lather with soap. It contains little to no dissolved minerals like calcium and magnesium, which are responsible for water hardness. Examples of soft water include rainwater, distilled water, and demineralized water. The next question is question number 14. What is hard water? Give examples. The answer to this question is hard water is water that does not form lather with soap, instead forming a white, curdy precipitate. It contains dissolved minerals such as calcium and magnesium bicarbonates, sulfates, and chlorides. Examples include river water, sea water, and well water. The next question is question number 15. Explain the concept of water hardness. The answer to this question is water hardness is the property of water that prevents it from forming lather with soap. It is caused by the presence of dissolved calcium and magnesium salts, primarily in the form of bicarbonates, sulfates, and chlorides. The next question is question number 16. Why doesn't hard water form lather with soap? The answer to this question is hard water contains calcium and magnesium ions, which react with soap, sodium stearate, to form an insoluble compound called magnesium or calcium stearate or the soap scum. This prevents the soap from forming a lather. The next question is question number 17. Write the chemical reaction between sodium stearate and magnesium sulfate in hard water. The answer to this question is the reaction between sodium stearate, soap, and magnesium sulfate, hard water impurity, is to C17H35COONa, sodium stearate, plus MgSO4, magnesium sulfate, giving you C17H35COO, whole twice Mg, magnesium stearate, plus Na2SO4, sodium sulfate. The next question is question number 18. What are the two types of water hardness? The answer to this question is the two types of water hardness are temporary hardness. This type of hardness is caused by the presence of dissolved bicarbonates of calcium and magnesium, Ca, HCO3, 2 and Mg, HCO3, 2. Permanent hardness. This type of hardness is caused due to the presence of dissolved chlorides and sulfates of calcium and magnesium, CaCl2, MgCl2, CaSO4 and MgSO4. The next question is question number 19. What is temporary hardness of water? The answer to this question is temporary hardness is due to the presence of bicarbonates of calcium and magnesium in water. It can be removed by boiling, as these bicarbonates decompose into insoluble carbonates, which can be filtered out. The next question is question number 20. What causes permanent hardness in water? The answer to this question is permanent hardness is caused by the presence of dissolved chlorides and sulfates of calcium and magnesium. It cannot be removed by boiling the water and requires chemical treatment for its removal. The next question is question number 21. How is temporary hardness removed from water? The answer to this question is temporary hardness can be removed by boiling the water. When boiled, the bicarbonates of calcium and magnesium decompose into their corresponding insoluble carbonates, which can then be filtered out. The next question is question number 22. Why can't permanent hardness be removed by boiling the water? The answer to this question is permanent hardness cannot be removed by boiling the water because the soluble salts responsible for causing the permanent hardness, such as chlorides and sulfates of calcium and magnesium, do not decompose into insoluble forms on heating. The next question is question number 23. What are the units used to measure water hardness? There are many units for measuring the hardness of water. However, water hardness is commonly measured using the following two Units. ppm, parts per million. It can be defined as the number of parts of calcium carbonate present per 1 million parts of water. mg/L inverse, milligrams per liter. It can be defined as the number of milligrams of calcium carbonate present per liter of water. The next question is question number 24. Define ppm as used in measuring water hardness. The answer to this question is ppm, parts per million, is a unit used to express the concentration of hardness-causing minerals in water. 1 ppm means 1 part of hardness-causing minerals per 1 million parts of water. The next question is question number 25. What is water softening? The answer to this question is water softening is the process of removing or reducing the concentration of dissolved calcium and magnesium salts, which cause hardness, from water to make it soft. Methods include boiling, for temporary hardness, lime soda process, and ion exchange. The next question is question number 26. How is temporary hardness removed by boiling? The answer to this question is when temporary hard water is boiled, the soluble bicarbonates of calcium and magnesium decompose into their corresponding insoluble carbonates. These carbonates precipitate out as solid sludge and can be removed by filtration. The reactions are CaHCO3 whole twice on heating gives you CaCO3 solid plus CO2 gas plus H2O liquid. MgHCO3 whole twice on heating gives you MgCO3 solid plus CO2 gas plus H2O L. This process effectively removes temporary hardness from water. The next question is question number 27. Explain the lime soda process for removing permanent hardness. The answer to this question is the lime soda process removes permanent hardness by adding calculated amounts of lime, CaOH, whole twice, and soda, Na2CO3, to hard water. The lime reacts with calcium bicarbonate to form calcium carbonate, and the soda reacts with magnesium bicarbonate to form magnesium hydroxide. Both calcium carbonate and magnesium hydroxide are insoluble precipitates, which can be filtered out, softening the water. Reactions involved: CaHCO3 to plus CaOH whole twice, giving you to CaCO3 solid plus to H2O. MgHCO3 to plus Na to CO3, giving you MgCO3 solid plus to NaHCO3. The next question is question number 28. What is the difference between cold and hot lime soda processes? The answer to this question is cold lime soda process, conducted at room temperature, 25 degrees Celsius, requires coagulants and produces water with a residual hardness of about 50 to 60 ppm. It is slower and less efficient. Hot lime soda process, conducted at temperatures between 80 to 150 degrees Celsius, is faster, produces water with lower residual hardness, 15 to 30 ppm, requires no coagulants, and removes dissolved gases. It is more efficient than the cold process. The next question is question number 29. What is the role of lime and soda in the lime soda process? The answer to this question is lime, CaOH, whole twice reacts with calcium bicarbonate in hard water, converting it into insoluble calcium carbonate, which can be removed by filtration. Soda, Na2CO3, reacts with magnesium bicarbonate and other salts, converting them into insoluble carbonates or hydroxides, example MgCO3 or MgOH, whole twice, which can be filtered out, softening the water. The next question is Question number 30. Describe the cold lime soda process. The answer to this question is: in the cold lime soda process, hard water is mixed with lime, CaOH, whole twice, and soda, Na2CO3, at room temperature, 25 degrees Celsius. The calcium and magnesium salts in the water react with these chemicals to form insoluble precipitates of calcium carbonate and magnesium hydroxide, which settle down as sludge. The soft water is collected after filtration, leaving behind the sludge. The next question is: question number 31. What is the principle behind the cold lime soda process? The answer to this question is: the cold lime soda process is based on the chemical conversion of soluble calcium and magnesium salts, responsible for water hardness, into insoluble compounds. These insoluble compounds, such as calcium carbonate and magnesium hydroxide, are then removed by filtration, leaving behind soft water. The next question is: question number 32. What apparatus is used in the cold lime soda process? The answer to this question is: the cold lime soda process uses a conical-shaped steel tank with an inner vertical circular chamber. The raw hard water, lime, and soda are introduced from the top. A rotating shaft with paddles mixes the water and chemicals. As the water softens, the precipitates, sludge, settle at the bottom, and the softened water rises to the top and is filtered through a wood fiber filter. The next question is: question number 33. List the disadvantages of the cold lime soda process. The answer to this question is: it is a slow process as the reactions take place at room temperature. Coagulants like alum are required to settle the precipitates. The process produces water with a residual hardness of about 50 to 60 ppm, which may not be suitable for some industrial uses. Dissolved gases are not removed from the water. The next question is: question number 34. Describe the hot lime soda process. The answer to this question is: in the hot lime soda process, hard water is treated with lime and soda at elevated temperatures, 80 to 150 degrees Celsius. The reactions occur faster due to the higher temperature, and the precipitates form more quickly. The water is then passed through a sedimentation vessel to remove the precipitates, sludge, followed by a sand filter to remove any remaining solids. The next question is: question number 35. What is the principle behind the hot lime soda process? The answer to this question is: the hot lime soda process involves treating hard water with lime, CaOH2, and soda, Na2CO3, at high temperatures. The higher temperature speeds up the reaction rate, reducing the time required to soften the water and ensuring more complete precipitation of the hardness-causing salts. The next question is: question number 36. List the advantages of the hot lime soda process. The process is faster and more efficient than the cold lime soda process. No coagulants are needed as the sludge settles easily. The water produced has a lower residual hardness, 15 to 30 ppm. Dissolved gases like CO2 and air are removed. Pathogenic bacteria are destroyed. Filtration is easier due to the reduced viscosity of water at higher temperatures. The next question is: question number 37. What is the residual hardness left in the cold lime soda process? The residual hardness left in the cold lime soda process is approximately 50 to 60 ppm, parts per million. The next question is: question number 38. What is the residual hardness left in the hot lime soda process? The answer to this question is: the residual hardness left in the hot lime soda process is much lower, around 15 to 30 ppm. The next question is question number 39. Why does the hot lime soda process work faster than the cold one? The answer to this question is the hot lime soda process works faster because the reactions occur at elevated temperatures, 80 to 150 degrees Celsius. Higher temperatures increase the reaction rate, allowing the precipitates to form more quickly and settle faster. The next question is question number 40. What type of coagulant is required in the cold lime soda process? The answer to this question is in the cold lime soda process, coagulants like alum, Al2, SO4, whole thrice are required to help the precipitates formed during the reaction settle down more effectively. The next question is question number 41. Why are dissolved gases removed in the hot lime soda process? The answer to this question is dissolved gases such as carbon dioxide, CO2, and oxygen, O2, are removed in the hot lime soda process because heating the water causes these gases to escape. The higher temperature reduces the solubility of gases, making them easier to remove. The next question is question number 42. What is ion exchange and how does it help in water softening? The answer to this question is ion exchange is a process in which undesirable ions in hard water, example calcium and magnesium, are exchanged with more desirable ions, example hydrogen or sodium, using ion exchange resins. This process effectively removes hardness by replacing calcium and magnesium ions with ions that do not cause hardness, resulting in soft water. The next question is question number 43. What are ion exchange resins? The answer to this question is ion exchange resins are organic polymers with a porous, permeable structure that contains ionizable functional groups, acidic or basic. These functional groups can exchange their ions with the ions in the water. The two main types are cation exchange resins contain acidic groups COOH, SO3H that exchange H plus ions for cations, example Ca2 plus, Mg2 plus. Anion exchange resins contain basic groups OH1 negative that exchange OH1 negative ions for anions, example Cl1 negative, SO42 negative. The next question is question number 44. Describe the structure of organic ion exchange resins. The answer to this question is organic ion exchange resins are high molecular weight polymers that have an open and permeable structure. Attached to the polymer backbone are ionizable functional groups, which are either acidic, cation exchange resins, or basic, anion exchange resins. These functional groups facilitate the exchange of ions between the resin and the water passing through it. The next question is question number 45. Differentiate between cation exchange resin and anion exchange resin. Cation exchange resin contains acidic groups like COOH or SO3H, which exchange H plus ions for metal cations such as calcium, Ca2 plus, or magnesium, Mg2 plus. Anion exchange resin contains basic groups like OH1 negative or NH2 negative, which exchange OH negative ions for anions like chloride, Cl1 negative, or sulfate, SO42 negative. The next question is question number 46. Describe the ion exchange process. The answer to this question is in the ion exchange process, hard water is passed through a column containing a cation exchange resin. The resin exchanges its H plus ions for the calcium and magnesium ions in the water. The water is then passed through a second column containing an anion exchange resin, which exchanges its OH1 negative ions for the anions Cl1 negative, SO42 negative. The H plus and O negative ions released combine to form water, H2O, resulting in deionized or demineralized water. The next question is question number 47. How is deionized water produced in the ion exchange process? The answer to this question is deionized water is produced by passing hard water through both cation exchange and anion exchange resins. The cation exchange resin removes cations, example Ca2+, Mg2+, and replaces them with H plus ions, while the anion exchange resin removes anions, example Cl1 negative, SO42 negative, and replaces them with OH1 negative ions. The H plus and OH1 negative ions combine to form pure water, H2O. The next question is question number 48. What happens during the regeneration of resins in the ion exchange process? The answer to this question is during the regeneration of resins, the exhausted cation exchange resin is regenerated by treating it with a dilute acid, example HCl, which replenishes the H plus ions. Similarly, the exhausted anion exchange resin is regenerated by treating it with a dilute alkali, example NaOH, which replenishes the OH1 negative ions. This restores the resin's ability to exchange ions and allows them to be reused. The next question is question number 49. Which chemicals are used for regenerating cation exchange resins? The answer to this question is cation exchange resins are regenerated by using dilute acids such as hydrochloric acid, HCl, or sulfuric acid, H2SO4. These acids supply hydrogen ions, H+, which replace the metal cations, Ca2+, Mg2+, that were absorbed by the resin during the softening process. The next question is question number 50. Which chemicals are used for regenerating anion exchange resins? The answer to this question is anion exchange resins are regenerated by treating them with dilute alkalis, typically sodium hydroxide, NaOH. The hydroxide ions, OH1 negative, from the alkali replace the anions, example chloride, sulfate, that were absorbed by the resin during the ion exchange process. The next question is question number 51. List the advantages of the ion exchange process. Produces water with very low hardness, as low as 2 ppm, making it suitable for high-pressure boilers. Can be used to soften highly acidic or alkaline water. Produces deionized water, which is free from both cations and anions. Suitable for producing water for pharmaceutical and laboratory purposes. The next question is question number 52. List the disadvantages of the ion exchange process. The answer to this question is the equipment is costly. Requires expensive chemicals for regeneration. Making it suitable for high-pressure boilers. Not suitable for water with high turbidity, as suspended particles can clog the resin and reduce its efficiency. Resin regeneration produces waste products, which need careful disposal. The next question is question number 53. What is the main disadvantage of the cold lime soda process? The answer to this question is the cold lime soda process is slow, as the reactions occur at room temperature, requiring a longer time for completion. Additionally, coagulants are needed to settle the precipitates, and the water produced has a higher residual hardness, 50 to 60 ppm, which may not be suitable for some industrial applications. The next question is question number 54. Why is the hot lime soda process more economical than the cold one? The answer to this question is The hot lime soda process is more economical because it operates at higher temperatures, speeding up the reactions and reducing the time required for softening. It also produces water with lower residual hardness, 15 to 30 ppm, without the need for coagulants, reducing chemical costs. The next question is question number 55. What happens to the sludge produced in the lime soda process? The answer to this question is the sludge formed in the lime soda process consists of precipitated calcium carbonate, CaCO3, and magnesium hydroxide, MgOH, whole twice. This sludge settles at the bottom of the reaction vessel and must be periodically removed and disposed of, which can be a logistical and environmental challenge. The next question is question number 56. Explain why coagulants are not required in the hot lime soda process. The answer to this question is coagulants are not required in the hot lime soda process because the higher temperature causes the precipitates, sludge, to settle more rapidly and completely. This reduces the need for coagulants, which are used in the cold lime soda process to facilitate sludge settling. The next question is question number 57. What are the typical operating temperatures for the hot lime soda process? The answer to this question is the typical operating temperatures for the hot lime soda process range from 80 degrees Celsius to 150 degrees Celsius. These elevated temperatures improve the reaction rates and the efficiency of the softening process. The next question is question number 58. What is the role of paddles in the cold lime soda process apparatus? The answer to this question is in the cold lime soda process, paddles attached to a rotating shaft stir the mixture of hard water, lime, and soda. This ensures that the chemicals are thoroughly mixed with the water, allowing the reactions to occur efficiently and evenly throughout the solution. The next question is question number 59. How does heating affect the efficiency of the hot lime soda process? The answer to this question is heating in the hot lime soda process increases the reaction rate between the lime, soda, and the hardness causing salts in water. This leads to faster precipitation of calcium carbonate and magnesium hydroxide, resulting in quicker and more complete water softening. Additionally, heating helps to remove dissolved gases and lowers the viscosity of water, making filtration easier. The next question is question number 60. What is the function of the sand filter in the hot lime soda process? The answer to this question is the sand filter in the hot lime soda process is used to remove any remaining solid particles, precipitated sludge, from the softened water after the main reaction has taken place. This ensures that the water coming out of the process is free from suspended solids and suitable for use. The next question is question number 61. How does the ion exchange process work for highly alkaline water? The answer to this question is in the ion exchange process, highly alkaline water can be softened because the cation exchange resin replaces the alkaline metal ions, example sodium, calcium, magnesium, with hydrogen ions, H+, which reduces the alkalinity. The anion exchange resin replaces the anions, example bicarbonate, carbonate, with hydroxide ions, OH1-, further balancing the pH and removing alkalinity from the water. The next question is question number 62. What is the residual hardness achieved through the ion exchange process? The answer to this question is the ion exchange process can reduce the hardness of water to extremely low levels, typically down to 2 ppm or even less, depending on the quality of the resins and the specific system in use. The next question is question number 63. Why is the ion exchange process suitable for high-pressure boilers? The answer to this question is: the ion exchange process is suitable for high-pressure boilers because it produces water with very low residual hardness, up to 2 ppm, which helps prevent scale formation in the boilers. This ensures efficient heat transfer and reduces the risk of boiler tube failure due to scaling. The next question is question number 64. Describe the regeneration process in the ion exchange method. The answer to this question is: the regeneration process in the ion exchange method involves restoring the ion exchange resins to their original form after they have been exhausted. For cation exchange resins, regeneration is done by treating them with a dilute acid, such as hydrochloric acid, HCl, to replace the metal cations, example Ca2+, Mg2+, with hydrogen ions, H+. For anion exchange resins, regeneration is done by treating them with a dilute alkali, such as sodium hydroxide, NaOH, to replace the absorbed anions, example Cl1-, SO42-, with hydroxide ions, OH1-. The next question is question number 65. How does turbidity in water affect the ion exchange process? The answer to this question is: turbidity in water, caused by suspended particles such as clay, silt, and organic matter, can clog the pores of the ion exchange resins, reducing their efficiency and lifespan. The suspended particles block the ion exchange sites, preventing proper ion exchange and reducing the effectiveness of the softening process. The next question is question number 66. Why is the ion exchange process more expensive than the lime-soda process? The answer to this question is: the ion exchange process is more expensive than the lime-soda process because it requires specialized equipment and high-quality resins, which need to be replaced periodically. Additionally, the chemicals used for regeneration, example acids and alkalis, are costly, and the system requires maintenance to prevent fouling and resin degradation. The next question is question number 67. What are the two types of underground water? The answer to this question is: the two types of underground water are spring water, water that naturally flows to the earth's surface from an underground source; well water, water that is obtained by drilling or digging into the ground to reach groundwater reserves. The next question is question number 68. What is the effect of hardness on industrial water usage? The answer to this question is: hard water can cause significant problems in industrial settings, such as scaling in boilers, heat exchangers, and pipes, reducing efficiency and increasing energy consumption. Increased soap and detergent consumption in cleaning processes. Potential damage to machinery and equipment due to the deposition of mineral scales. Reduced lifespan of water-based systems. The next question is question number 69. Explain how magnesium and calcium salts cause water hardness. The answer to this question is: magnesium and calcium salts, such as magnesium bicarbonate, Mg, HCO3, 2, calcium bicarbonate, Ca, HCO3, 2, magnesium sulfate, MgSO4, and calcium chloride, CaCl2, dissolve in water and release Mg2+ and Ca2+ ions. These ions react with soap, forming insoluble compounds that prevent lather formation and cause scaling in pipes and boilers. The next question is question number 70. What are the common sources of dissolved gases in natural water? The answer to this question is: the common sources of dissolved gases in natural water include atmospheric gases such as oxygen, O2, and nitrogen, N2, which dissolve in water during contact with the air. Biological processes, such as respiration and decomposition, which release gases like carbon dioxide, CO2, and methane, CH4. Volcanic or geothermal activity, which may release sulfur dioxide, SO2, or hydrogen sulfide, H2S, into nearby water bodies. The next question is question number 71. Why is rainwater slightly acidic? The answer to this question is rainwater is slightly acidic because, as it falls through the atmosphere, it dissolves gases like carbon dioxide, CO2, sulfur dioxide, SO2, and nitrogen oxides, NOx smiley. These gases react with water to form weak acids such as carbonic acid, H2CO3, sulfurous acid, H2SO3, and nitric acid, HNO3, making the rainwater slightly acidic. The next question is question number 72. What are the common biomaterials found in seawater? Seawater contains various biomaterials, including carbohydrates, proteins, amino acids, and lipids, which originate from marine organisms like algae, plankton, and bacteria. These biomaterials contribute to the complex chemical composition of seawater. The next question is question number 73. How does the ion exchange process produce demineralized water? The answer to this question is the ion exchange process produces demineralized water by passing hard water through cation exchange and anion exchange resins. The cation exchange resin removes cations like Ca2+ and Mg2+, replacing them with H+ ions, while the anion exchange resin removes anions like Cl1- and SO42-, replacing them with OH1- ions. The H+ and OH1- ions combine to form pure water, H2O, leaving behind demineralized water. The next question is question number 74. What is the role of H+ and OH1- ions in the ion exchange process? The answer to this question is in the ion exchange process, H+ ions from the cation exchange resin replace the metal cations, example Ca2+, Mg2+, in hard water, while OH1- ions from the anion exchange resin replace the anions, example Cl1-, SO42-. The H+ and OH1- ions released during this process combine to form water, H2O, resulting in demineralized water. The next question is question number 75. What are the common anions found in hard water? The answer to this question is common anions found in hard water include chloride, Cl1-, sulfate, SO42-, bicarbonate, HCO3-1-, nitrate, NO3-1-. The next question is question number 76. What are the common cations found in hard water? The answer to this question is common cations found in hard water include calcium, Ca2+, magnesium, Mg2+, sodium, Na+, potassium, K+. The next question is question number 77. What is the significance of removing hardness in water for household purposes? The answer to this question is removing hardness from water is important for household purposes because hard water causes soap to be less effective, leading to higher detergent use. It leads to scaling in plumbing systems and appliances, reducing their efficiency and lifespan. Hard water can leave spots and stains on dishes, clothing, and fixtures. Soft water improves cleaning efficiency and reduces maintenance costs. The next question is question number 78. What is the economic impact of using hard water in industries? The answer to this question is: using hard water in industries can lead to increased energy consumption due to scaling in boilers and heat exchangers, reducing heat transfer efficiency. Higher maintenance costs for cleaning or replacing equipment affected by scale. Increased consumption of detergents and chemicals in cleaning processes. Production inefficiencies and potential downtime due to equipment failures caused by scaling. The next question is question number 79. How does the hardness of water affect soap consumption? The answer to this question is: hard water increases soap consumption because the calcium and magnesium ions in the water react with soap to form insoluble compounds, scum, reducing the soap's ability to lather and clean effectively. As a result, more soap is needed to achieve the same cleaning effect. The next question is question number 80. What is the importance of removing dissolved gases from water? Removing dissolved gases from water is important because gases like oxygen, O2, and carbon dioxide, CO2, can contribute to corrosion in metal pipes and equipment. In industrial applications, dissolved gases can affect chemical reactions or lead to scaling and fouling in boilers and heat exchangers. In water treatment, removing gases can improve the quality and stability of treated water. The next question is question number 81. Describe the sludge produced during the lime soda process. The answer to this question is: the sludge produced during the lime soda process consists mainly of insoluble precipitates such as calcium carbonate, CaCO3, and magnesium hydroxide, MgOH, whole twice. These precipitates form when calcium and magnesium ions in hard water react with the added lime, CaOH, whole twice, and soda ash, Na2CO3, during the softening process. The sludge settles at the bottom of the treatment vessel and must be periodically removed to prevent clogging and ensure efficient water treatment. It is often thick and heavy due to the high density of the precipitates. The next question is question number 82. Why is filtration necessary after water softening processes? The answer to this question is: filtration is necessary after water softening processes to remove the insoluble precipitates, sludge, formed during the treatment. In processes like the lime soda process, calcium carbonate and magnesium hydroxide are precipitated out, and these solid particles must be filtered from the water to prevent clogging of pipes, boilers, and other equipment. Filtration ensures that the softened water is free of suspended solids, making it suitable for industrial and domestic use. It also improves the clarity and overall quality of the water. The next question is question number 83. What happens to the bicarbonates of calcium and magnesium upon heating? The answer to this question is: when water containing bicarbonates of calcium, CaHCO3, 2, and magnesium, MgHCO3, 2, is heated, these bicarbonates decompose into their corresponding carbonates and release carbon dioxide, CO2, gas. The reactions are as follows. Calcium bicarbonate, CaHCO3, on heating gives you CaCO3, solid, plus CO2, gas, plus H2O, L. Magnesium bicarbonate, MgHCO3, on heating gives you heat MgCO3, solid, plus CO2, gas, plus H2O, L. The solid carbonates, CaCO3 and MgCO3, precipitate out as sludge, while carbon dioxide gas is released, softening the water by removing temporary hardness. The next question is question number 84. What are the potential health impacts of drinking hard water? The answer to this question is: drinking hard water is generally not considered harmful to health and, in some cases, may provide a source of essential minerals like calcium and magnesium. However, excessive hardness can lead to digestive issues in some people due to high mineral content. Scaling in the plumbing systems of homes, leading to the release of metal contaminants, such as lead from pipes, into drinking water. Reduced efficiency of water heaters and kettles, causing frequent repairs or replacements. Very high hardness levels could also affect taste, making water unpalatable for drinking. The next question is question number 85. Explain the role of sodium carbonate in the lime soda process. The answer to this question is: sodium carbonate, Na2CO3, commonly known as soda ash, plays a crucial role in the lime soda process by removing magnesium hardness. In hard water, magnesium is typically present in the form of bicarbonates or sulfates. Soda ash reacts with these magnesium salts to form magnesium carbonate, MgCO3, which is either insoluble or partially soluble, precipitating out as solid sludge. The reactions are as follows: MgSO4 plus Na2CO3 giving you MgCO3, solid, plus Na2SO4. The sodium carbonate also helps in removing calcium hardness when combined with lime, CaOH, whole twice. The next question is question number 86. How is the hardness of water related to boiler scale formation? The answer to this question is: hardness in water is directly related to boiler scale formation. When hard water is heated in boilers, the calcium and magnesium bicarbonates decompose, forming insoluble calcium carbonate, CaCO3, and magnesium hydroxide, MgOH, whole twice. These precipitates settle on the inner surfaces of the boiler, forming a hard, crusty scale. This scale reduces the efficiency of heat transfer, leading to higher fuel consumption, potential overheating, and damage to boiler tubes. Over time, thick scale deposits can cause blockages and boiler failure, making water softening essential for boiler operations. The next question is question number 87. What is the significance of the ion exchange process in the pharmaceutical industry? The answer to this question is: the ion exchange process is highly significant in the pharmaceutical industry because it produces demineralized or ultra-pure water, which is essential for various applications, including preparing pharmaceutical products where impurities can affect the efficacy of drugs, cleaning and sterilizing equipment to avoid contamination, making injections and intravenous solutions that require water free from minerals, bacteria, and other impurities, providing high-purity water for laboratory testing and chemical synthesis, where water quality directly impacts experimental results. The next question is question number 88. Why is soft water essential in steam generation? The answer to this question is: soft water is essential in steam generation to prevent scaling inside boilers and steam turbines. Hard water, which contains calcium and magnesium salts, can form solid deposits, scale, when heated, reducing the efficiency of steam generation by insulating the heat transfer surfaces. Scaling can also lead to overheating, corrosion, and eventual failure of the boiler or turbine components. By using soft water, industries ensure that boilers operate efficiently and safely, reducing maintenance costs and prolonging the life of the equipment. The next question is question number 89. How do dissolved minerals affect the taste of drinking water? The answer to this question is: dissolved minerals in water, such as calcium, magnesium, sodium, and chloride significantly affect the taste of drinking water. Calcium and magnesium give water a slightly bitter or chalky taste, which can be more pronounced at higher concentrations. Sodium adds a salty taste to water, which can become unpalatable at high levels. Chlorides and sulfates can also give water a salty or metallic taste. While low levels of dissolved minerals can enhance the taste of water, high concentrations can make the water taste unpleasant. The next question is question number 90. What are the different methods used for water purification? The answer to this question is common methods for water purification include filtration, removing suspended particles through sand, activated carbon, or membrane filters. Boiling, killing bacteria, viruses, and other pathogens by heating water. Chlorination, adding chlorine to kill microorganisms. Ion exchange, removing dissolved minerals responsible for hardness, calcium and magnesium. Reverse osmosis, forcing water through a semi-permeable membrane to remove dissolved salts and impurities. UV sterilization, using ultraviolet light to kill or inactivate pathogens. Distillation, evaporating water and condensing the vapor to remove dissolved solids and impurities. The next question is question number 91. What role does temperature play in water softening processes? The answer to this question is temperature plays a significant role in water softening processes. In the hot lime soda process, higher temperatures, 80 to 150 degrees Celsius, speed up the reactions between lime, soda, and hardness causing salts, leading to faster and more complete precipitation of calcium and magnesium compounds. Hotter temperatures also reduce the viscosity of water, improving filtration and sludge separation. Temperature also influences ion exchange processes, as the efficiency of ion exchange increases with higher temperatures up to a certain limit. Higher temperatures reduce the solubility of certain salts, aiding in more effective softening. The next question is question number 92. Explain how dissolved gases are removed in the hot lime soda process. The answer to this question is dissolved gases, such as carbon dioxide, CO2, and oxygen, O2, are removed during the hot lime soda process through heating. As the temperature of the water rises, the solubility of these gases decreases, causing them to escape from the solution. The release of CO2 is particularly important because it can contribute to corrosion in boilers and pipes. The hot lime soda process, by operating at elevated temperatures, ensures that these gases are efficiently driven out of the water. The next question is question number 93. Why is the ion exchange process not suitable for turbid water? The answer to this question is the ion exchange process is not suitable for turbid water because suspended particles in turbid water can clog the ion exchange resin beads, reducing their effectiveness. The turbidity blocks the active ion exchange sites, preventing proper ion exchange and reducing the system's efficiency. Additionally, the organic matter and colloidal particles in turbid water can foul the resins, requiring more frequent maintenance and regeneration. Prefiltration is often needed to remove turbidity before using ion exchange systems. The next question is question number 94. What is the role of sodium hydroxide in regenerating anion exchange resins? The answer to this question is sodium hydroxide, NaOH, is used to regenerate anion exchange resins by replenishing the hydroxide ions, OH1 negative, that are exchanged for anions, example chloride, sulfate, during the ion exchange process. When the resin becomes saturated with anions, it can no longer function effectively. Treating the resin with a dilute NaOH solution replaces the absorbed anions with OH1 negative ions, restoring the resin's ability to exchange ions and continue removing anions from the water. The next question is question number 95. What are the long-term effects of using hard water in household plumbing? The answer to this question is long-term use of hard water in household plumbing can lead to scale buildup. Hard water leaves behind calcium and magnesium deposits in pipes, reducing water flow and causing blockages over time. Increased energy consumption. Scale in water heaters and boilers reduces their efficiency, leading to higher energy bills. Corrosion and leaks. Deposits can cause localized corrosion, weakening pipes and fixtures, eventually leading to leaks. Shortened lifespan of appliances. Appliances like washing machines, dishwashers, and water heaters can suffer damage from scaling, reducing their efficiency and lifespan. The next question is question number 96. What are the chemical reactions involved in the removal of temporary hardness? The answer to this question is temporary hardness is removed by heating water, which causes the decomposition of calcium and magnesium bicarbonates into their corresponding carbonates. The reactions are calcium bicarbonate CaHCO3 to on heating gives you CaCO3 solid plus CO2 gas plus H2O magnesium bicarbonate MgHCO3 to on heating gives you MgCO3 solid plus CO2 gas plus H2O. These reactions result in the formation of insoluble carbonates CaCO3 and MgCO3, which precipitate out as sludge and can be removed by filtration. The next question is question number 97. Why is it important to remove both cations and anions from hard water? The answer to this question is it is important to remove both cations, example calcium, magnesium, and anions, example chloride, sulfate, from hard water because cations cause scaling and hardness, leading to inefficiencies in boilers, heating systems, and household appliances. Anions like chloride and sulfate can contribute to corrosion and scaling in pipes and equipment. They can also affect the taste of water and interfere with certain industrial processes. Removing both types of ions ensures that the water is soft and free from contaminants that could cause damage or operational problems. The next question is question number 98. What is the significance of using demineralized water in laboratories? The answer to this question is demineralized water is significant in laboratories because it is free of dissolved salts, minerals, and impurities, making it ideal for sensitive experiments where even trace amounts of contaminants can affect results. Preparing chemical solutions, ensuring that no unintended ions interfere with reactions. Cleaning laboratory equipment, preventing the deposition of minerals, which can alter the outcomes of experiments or damage instruments. Calibration of instruments. Demineralized water provides a stable, contaminant-free baseline for instrument calibration and testing. The next question is question number 99. What are the environmental concerns related to the disposal of sludge from water softening? The answer to this question is the disposal of sludge from water softening processes, such as the lime soda process, presents several environmental concerns. Land contamination. Improper disposal of sludge, which contains high levels of calcium and magnesium compounds, can lead to soil contamination and affect plant growth. Water pollution. If sludge is not properly contained, it can be washed into nearby water bodies, altering the pH and causing harmful effects on aquatic life. Disposal costs. The sheer volume of sludge produced in large-scale water treatment facilities requires careful planning for transportation and disposal, leading to higher operational costs. Toxicity. In some cases, sludge may contain traces of harmful chemicals used during the water treatment process, which could pose a risk to the environment if not disposed of properly. The next question is question number 100. Explain why the hot lime soda process is faster than the cold lime soda process. The answer to this question is the hot lime soda process is faster than the cold lime soda process because higher temperatures increase the reaction rates between lime, soda, and hardness causing salts, allowing the reactions to proceed more quickly and completely. Reduced viscosity. At higher temperatures, the viscosity of water decreases, which facilitates better mixing of chemicals and faster settling of the precipitates, calcium carbonate and magnesium hydroxide. Dissolved gases removal. Gases like carbon dioxide, which can interfere with the precipitation process, are expelled more easily at higher temperatures. Pathogen destruction. High temperatures also kill any bacteria present, improving the overall quality of the water more rapidly. The hot process achieves greater efficiency in a shorter time frame, making it the preferred method for large-scale industrial water softening. I hope you have liked the video. If you found this video informative and helpful in learning the topic easily and simply, then like, share and subscribe to our channel. Gyan Vigyan 09. We will come back soon with similar informative and educational videos to make your learning process easy and simple. Thanks for watching. Goodbye.